Hi, I'm Gilbert Park, an assistant professor at Hong Kong Polytechnic University. I'm responsible for AF6005, a core course for first-year PhD students, which is titled Microeconomic Foundations of Financial Economics. In the course, we start from microeconomic principles to modern topics in finance. It includes preference and choice, risk and uncertainty, basic game theory, modern portfolio theory, and aero-debris economy, to name a few topics that we cover in class. Due to the structure of the course, it requires some mathematical background. For those who are less familiar with mathematics, I also provide lectures of mathematics that are required to understand theories dealt in class. Upon completing the course, I expect the students to be able to understand theoretical concepts of the finance theories, and the course will also provide a base to understand more advanced theories in finance and economics. First is called the Elias paradox. Okay, so paradox, you can see that, oh, there's some kind of problem or something. Yes, this example shows you a problem with the expected utility theorem. Now let's look at this example. Okay, and even though if you didn't understand the expected utility, maybe this helps you understand the expected utility too, this example. Now, suppose there are 4 lotteries. Actually, I'm going to show you 5, but let's first see the first 4. Lottery 1, you get $10,000 with probability 0.1, which is 10%, and 0 otherwise, which means 90% of the time you get 0. 10% you get 10,000. L2, you get 15,000 with probability 0.09 and 0 otherwise. L3, you get 10,000, probability 1, which is sure, okay? And 0 otherwise. L4, 15,000 with 90% and 10% you get nothing. And then there's another lottery, L0, that always gives you 0. Okay, now let's do a survey. Everyone has to type in, okay, to see if you are awake. If there's L1 and L2, which one would you prefer? Would you prefer a lottery that gives you $10,000 with 10%? Or $15,000 with 9%. Type in, okay? I'll see what you guys think. Okay. There's no right or wrong answer here, okay? Just in case, there's no right and wrong. There's only 5 of you who responded. Okay, from time to time, I'm going to ask you these kind of questions, so I can see who's listening. Okay, but of course I'm not going to. For our class, I don't care about attendance really, but okay. Most of you or all of you picked 2. Fine. Now, how about 3 and 4? Okay. Would you prefer? Okay. This is last year. Some people kind of said this was too little. This is, let's say this is US dollars, not Hong Kong dollars. Okay. 10,000 US dollars with for sure, or $15,000 with 90% of the chance. Which one would you prefer? 3 or 4? 3. Four. Okay, there's 1 4. Okay, again, there's no. Okay. For any one of you, I don't need to hear from anyone. Why would you pick 3 over 4 for those who pick 3? Can anyone type in or say through the microphone? Why do you pick 3?
Hello, Professor.
Yes.
I chose 3 is because there is no way to lose. But if I choose 4, there is like 10% chance I might have nothing.
Okay,
so
good. Good.
Okay.
Fangqin, why did you choose 4? You're the only one who chose 4.
Because the expected value is higher.
Okay, good. Okay, see, so both are very good arguments. Okay, good. But okay, so if you do an experiment, most people will choose 3, but there are people who choose 4. But then notice that if you mix L0 and L3, okay, how do you mix L3 and L0? So I'm going to give you 0.1 L3 and then 0.9 L0, okay? And then you, with the same fraction you do with L4, 0.1 L4 plus, I should have typed it instead of drawing it again. Now if you do this, this is same as L1. This is same as L2. Now if you understand something that we have gone over, you see where this is going. Notice that most people prefer L2 over L1. This thing, how you have mixed. Most people, not all, okay? Most people prefer L3 over L4. Oh, not 4, L4. L4. If we have independence, mixing it with something, okay, mixing with the same thing, same fraction, you should keep the preference, which means this is L2, L1, okay? You should have this preference to be lined up. But that's not the case. Most people, not all, most people would prefer L3 over L4, but L2 over L1. So it seems like independence does not work. Although we think that was a pretty much desirable characteristic of a preference. And if you go back, if you want to use the expected utility function, notice that this is an if and only if condition, which means you need to have your preference over lotteries to be independent. We're satisfying the independence axiom. However, according to this example, and if you do a survey or if you do an experiment, you find that the independence does not hold. In other words, expected utility theorem works if independence holds, but people don't have independence axiom to be satisfied. So it seems like a very wrong utility function that people are playing around with, right? So why are we still using expected utility theorem, which is based on a wrong axiom? Okay, that's the people that's the argument that the people who are against the expected utility theorem, and that kind of the explanation is in this slide. You can read it. So in some cases, so if we relax some of the assumptions, we have some other expected utility function that's not the von Neumann-Morgenstern expected utility. Okay. The problem is, one of the reasons that this experiment fails is due to that linearity assumption that independence kind of gives you. And this is something that may be related to you regret. Why? Because if you go back, okay, if I choose L4, okay, people choose L3 because they always win, okay? If you choose L4, 90% you win, but let's assume you face a case 10% of losing. Then you sometimes regret, right? Oh, I should have chosen L3 in that case. No, I could have won at least 10,000, but because I took that kind of risk, I haven't introduced what risk is, but let's assume that you kind of know what that is, but because I chose that risk, I lost 10,000, which I could have had. Okay, that's regret, right? Because you're saying, oh, I should have done something. That's all related to this paradox, okay? And this, again, this part is just the explanation of what we did. And there are more examples, okay? But then I'm going to introduce something that kind of gets away with the von Neumann-Morgenstern utility function problem.